We stopped over here. Now, is anybody from Scotland over here? Scotland. You know, freedom and okay, because I have this example. So you know, we introduced machinery that allows for a multi-filtration. And that's just a toy example and something that looks Scottish. So we have 3 channels over here, which happens to be red, green, and blue, or as you use our RGB channels, and can define a filtration. And in this case, the Euler characteristic profile will be a function defined over a 3-dimensional space. So something that in principle we cannot visualize, but we can compute the distances between them. And we did it over here. So let me zoom it for you. So that is a distance matrix between those characteristics. And what you can see, what you can read out from the distance matrix is, first of all, I mean, among the type of, let's say, fabric of the same topology, they are kind of closer together. And they are farther away from the fabric of different topology. So that's observation number 1. But if you look, for instance, at the distance of that fabric from this one, I mean, they're kind of closer together, and this one and the other 2. And again, that's because they are sharing the same color. So so if we just use, you know, the machinery of Euler profiles for filtration having 3 values, kind of makes sense. So this is a toy example, Scottish one. And now in Poland, we used to have this Scottish book in both, when you put a mathematical problem. So I have a Scottish example. It's a Polish tradition to have something Scottish. Okay, somebody asked me. You asked me about the medical data. Yeah, okay. Can get the candy. So when I mention RGB, immediately that should ring a bell that we can do something with colored images. That's one of the examples that we are actually considering in this paper. So it's a toy example, kind of motivated by a paper of Olivier Vipon that co-authors, where they are looking at histology slices from prostate cancer. And we have a regression problem. So we are trying to assign this Gleason scale, and which kind of characterize how aggressive the tumor is. So the higher the Gleason scale, the worse the tumor is, the more aggressive, and the worse for the patient. And what the histologists are doing, well, they were looking at the microscope and just, you know, assign. So if you look at the paper, you can find the data set, and it's actually processed in the way that you process it with 2 chemicals. One is called hematoxylin, and the other one is called eosin. And you know, that's the thing which is processed with hematoxylin, and the same thing processed with eosin. You see different aspects of cells and the cell boundaries of the thing. But what we can do, you know, given that image, we can just threshold it. So we can bring the values on the 2 channel into 1 channel. There is no unique way of doing it. So over here, we use something standard off the shelf. And once you have a grayscale image, you can compute the Euler character, for instance, Euler characteristic curve. You can also compute persistent homology. And you can use it to try to solve the regression problem. And once you do it, for that particular data set, we are getting an accuracy of around 75%. The biggest confusion between class 3 and 4. So those are the most aggressive tumors. And the question whether it's good or not, I don't know. This is a data set annotated by the human. So it's subjected to bias of the people who are annotating it. And especially, I mean, you know, when there is this high risk of very bad cancer, I'm pretty sure that people kind of tends to exaggerate in order for the patients to get better treatment to increase the chances. The question whether this number is good or not, I mean, okay. But that's again based on the thresholding and having a standard one variable filtration and the Euler curves. You can also use persistence diagrams over here. I'm sorry, my throat is slowly dying today, so I'll try my best. But there's another way. So you can actually take the value of the pixel by hematoxylin and the same value as an eosin and treat it as a two separated channels, very much like red and green in the standard images. And once you do it, so that's the Euler characteristic profile for that particular image. And those profiles we can compare and we can vectorize and you can use in the regression. So over here we did a random forest regression, resulting roughly in 85% of accuracy. So taking two channels instead of one allows us to increase the accuracy by roughly 10% on this particular very small data set. So that's one of the examples of what we can do if we are able to somehow treat the multi-filtrations topologically. And actually, we are about to, so one of my postdocs is actually running a comparison on that particular data set of topological characteristics, followed by either support vector machines or CAD-boost or random forest versus the pre-trained convolutional neural networks. So from the literature, it seems that convolutional neural networks are roughly getting those results, but we haven't yet compared on that particular data set. So we kind of hope and finger crossed that we'll get a similar performance. And then, with topological methods, I mean, that's fully explainable. So we know, can explain every step, both in the extraction of Euler profiles and also in support vector machines regression, for instance, unlike for the neural networks. And I think that may be one of the bigger punchline of topological data analysis extracted features in comparison to predominant nowadays neural network based approach. So again, we are much less black boxy compared to the neural network based methods. And I hope next time I will be able to report something good. We'll see. So, as with many of our stuff, so I mentioned goodies from my previous life as a postdoc. Right now, we are also developing those libraries. We can quite easily access them in Python by simply pim installing them. If you go over here to our center GitHub, you can find some examples. I won't be doing examples, all of them, because simply we will be running out of time very quickly. So, that's a nice alternative. I think not quite yet explored to standard persistent homology. Then I encourage you to use. If you have any problems, any suggestions about the code, write us. We're trying to adjust it. So that's kind of the way we are working in the center. So we are trying to solve a problem, building up theory, building up proofs, in this case about the stability of stuff, but also trying to deliver the implementation as well as we can. So I encourage you to take a look at the examples. All the examples that I showed you, you can actually run over there, have all access to all the data sets, so you can check by yourself how it works. Again, in the interest of time, I won't be doing it unless we have tomorrow some time left. And I want to change the gears. So I started by motivating topology as a way of extracting better types of statistics, or types of statistics that kind of care about the shape of the data. And I want to take it back to statistics and try to use topology in some standard problem, which in this case is the goodness of fit. So I know there are some statisticians in the room, so please correct me if I'm saying something stupid. because I want to introduce statistics 101 without actually ever going through a statistics 101. So that's the goodness of fit test. And I prefer Wikipedia. You know, I really think it was epic. You should have another T-shirt saying not about Google, but about Wikipedia. Okay, so when we are speaking about the goodness of fit test, we have two types of problem: one sample and two sample. So in the one sample case, we have one sample, so a collection of points. Each of them lives in some d-dimensional space, and we also have a cumulative distribution function. And we are asking whether this collection of points follow the distribution or not, in which case we are formulating the null hypothesis H0 that it follows, and the alternative hypothesis, which is the negation of the null hypothesis. We are trying to see if we can reject the null hypothesis or not. So to my understanding, that's a standard setup. In the two sample test, it's kind of similar, but we don't have a cumulative distribution function, but we have two finite samples from two different distributions, and we are asking whether those two distributions are equal or not, based on the finite sample. And if you are ever solving this type of problems, the availability of tools really depends on D. So from what I know, if D is low, say equal 1, very standard problem. You get standard tests, Kolmogorov-Smirnov, Kramer for Mrs. Anderson, Darling, chi-square, and many, many more. But if you're starting to have a data from much higher dimensions, then availability of choice is kind of going down. And 2D, there are some theoretical results and some implementations for KS and Kramer for Mrs. But, you know, above 2, things are getting problematic, calls are getting slower. Yet this is where most of the application lives. So in most cases, I actually very rarely I encounter problems where our data samples are in so low dimensions, and typically they are in much higher dimensions. And this is where we are trying to use the advantage of topological characteristics. And kind of our inspiration was the Kolmogorov-Smirnov test, which I try to briefly discuss over here, at the bottom of the slide. So with the Kolmogorov-Smirnov, we are looking at the cumulative distribution function, this F, and it's the nice red curve. And based on the sample, so over here again we assume that D is equal 1. So based on the sample, we are building this this experimental distribution function, which is in blue. So if we have n points in the sample, you know, at every point we are looking how many points from our point cloud X, from our sample X, are to the left from a given point, and divided by n, by the cardinality of the whole thing. And once we have this continuous and the experimental cumulative distribution functions, we are looking at the maximum norm or L infinity distance between those two. And the magic behind Kolmogorov-Smirnov test, which I've been discussing, I still cannot understand, or I'm still amazed by the fact, is that, so this is the value of the statistics, so the L infinity distance between those two curves, and depending on how big it is, you can either reject or not be able to reject the null hypothesis, and it's kind of independent from the distribution. So it's, you know, a number, which is magic for me. It's extremely nice. But the problem with KS, do I have another slide? Yes. So yes, so in case of two sample problem, similar story, you are comparing just, you know, two experimental cumulative distribution functions. The problem with KS is that building those cumulative distribution functions in high dimensions is getting problematic. So it does generalize, but the complexity is pretty nasty. So our idea is very simple. We'll do something similar. Instead of cumulative distribution functions, put the topological characteristics. And because I spent the last hour speaking about Euler characteristic curve, you probably may be guessing what I am going to put over here. That's one reason. Well, it's something easy, one-dimensional, and the second reason is actually we can prove something, at least in the limit case. So we know some properties of the tests. So what's wrong? So let me introduce to you this family actually of methods which we call topological tests or topo tests for short, and tell you how it works and then show how it performs compared to the standard methods. So our input is very much like in the standard one or two sample case. So in the one sample we have a collection of points, the cumulative distribution function. And the topo test actually works in the 3 steps. So in the step, oh yeah, so as I plot you one nice animation and let me run it, and then I can jump to the next slide. Yeah, I do consider this slide justified. Okay, so in the first step, we want to understand how a sample of a size n from this cumulative distribution function, what the expected Euler characteristic of a sample of a size n from this cumulative distribution function looks like. And we are trying to get this thing essentially by Monte Carlo. So we are sampling a lot of samples of the size n, and then we are computing the average. So each of them, each sample gives Euler, it gives a curve. An average will be a curve. And I will consider it a blueprint of this cumulative distribution function for a sample size n. Question? No. So that's step number 1. So we know the average behavior. In the step number 2, we want to understand the variation. So if I sample a few more samples of a size n, how far away they can be from the average. So that's precisely what we are doing over here. So we are having a few more sample of the size n. For each of them, we compute standard characteristics, and then we are computing L infinity distance between the Euler curves of those additional samples and the average Euler characteristic curve, which we have from the previous step. And then we are fixing the significance level alpha. And we are sorting those distances, and we determine the critical value, the critical threshold, as the appropriate quantile of those distances. That's step number 2. So we know where majority of the Euler characteristic curve sampled from the same cumulative distribution function, where they live, how far away they can be from our sample, our average Euler characteristic curve. And step number 3 is the easiest one. So actually we are doing testing. So what you probably realized during the first 2 steps, we didn't touch this. So the only information we took from our sample is the size of the sample. We never actually work on the points. So right now it's the time to take points on board. So right now we are computing the Euler characteristic curve of our input sample of points. So this guy. Compute the L infinity distance between the Euler characteristic curve of the sample of points and our expected Euler characteristic curve. If it's above the critical value we get from step number 2, we reject the null hypothesis. Otherwise, we don't have a reason to reject the null hypothesis. That's all it is. So what I'm saying is replace cumulative distribution function with Euler curve. So over here you see Euler characteristic curves, average Euler characteristic curves for some family of distributions. We're not comparing cumulative distributions, we are comparing Euler curves. I'll come back to this in a second. They look quite different, so maybe there is a chance, maybe there is a potential. So this method doesn't care about the dimensionality of your data, doesn't care about the form of probability distribution function, just need to be able to sample from it. It works reasonably well in higher dimensions. We have some theoretical results. I will briefly discuss them in a second. It's more a framework rather than a particular test, and it actually overperforms standard tests, including KS, even in the low dimensions. And I'll be discussing some of the examples pretty soon. It has some caveats that you need to be aware of. So it's a matter of, it's the topological methods. So topology doesn't care about point cloud being translated, rotated, reflected, coordinates being reordered. Topology is fully blind to this type of things, which you may consider an advantage or a handicap. Depends how we approach it, but that's something to be aware of. For instance, those two distributions, when you have shifted and rotated two-dimensional normal, of course, Kolmogorov-Smirnov will clearly tell you that they are different topological tests. As I presented it, it will tell you that they are the same. So that's something to be aware of. And we do have some theoretical guarantees. And that's actually, we are exploring the fact that I mentioned, so that the Euler number actually appears in many branches of mathematics. So there is a lot of theoretical work done on the Euler numbers, unlike, for instance, for persistence diagrams. We do take advantage of some of the inequalities that we get over there. So for instance, we know we can estimate the probability of type 2 error, which is for a fixed significance level, the probability that we fail to reject null hypothesis when we actually should reject it, when it is false. I mean, we want this probability to go to 0 as our sample size goes to infinity. And that's indeed the case. We have an estimate of how quickly it goes to 0 in the limit. So that's something we are able to prove. We are able to do it on the two-sample case, in which case we are using the machinery of permutation tests. So the whole pipeline is, we have those two samples. We compute their Euler characteristic curves and the distance. Then we put them all to the same basket and then shuffle it, resample, and compute the Euler characteristic curves of those resampled things, compute their distance. Then we check how often after we reshuffle we get a larger or smaller distance. So we are doing standard, very expensive permutation tests, but it's also kind of helpful. I'll show one example from a spatial statistics, and I mean, it also has a reasonable power, so I'll get to this in a second. So it's both. So this approach is good for both one and two sample problems. So one thing to be aware of, we are comparing Euler characteristic curves, not the cumulative distribution function, which is kind of what I discussed over here. Method may be blind to some things, but there's a natural question. I mean, which types of distribution do we even have a chance to tell apart? There's actually a very nice result by Niklas, my PhD student, almost actually defended. He should be defending pretty soon, and his colleague, Tobias, and they actually were able to prove that if two cumulative distribution, if the two distributions have under some mild conditions, if they have the same exit mass transform, so the amount of mass that is above certain value t is the same for both distributions for every t, then they will have the same expected Euler characteristic. So those types of distribution we will not be able to tell apart. In practice, well, that's pretty rare situation, at least from what we see. So we know where we are not going to be successful for sure. So we actually then would like to discuss a practical validation of the method. So I will be using this concept of the test power, excuse me, which is the probability then the null hypothesis is rejected where it should be rejected. So if the null hypothesis is false, we want to reject it. So we want this probability to be as close to 1 as possible. And we estimate it by actually sampling from a very large collection of sample distributions, looking at various sample size. And for each sample size and for each pair of distribution, we did a 1,000 Monte Carlo repetition. So in this case, what do you expect? You expect, if you are comparing a distribution with itself, you expect the test to reject the H0 on the alpha % of times, which is the significance level. That's from the design of the method. We are also included in the collection of our distributions, the types of distributions which are easy to confuse, for instance, with a normal distribution like a T-student with various degree of freedom, multi-valued normal, Cartesian products, which has normal marginals. You know that there were quite a lot of energy going into this, so we use a Google infrastructure to do this Monte Carlo simulation. So I'll try to motivate that actually we look better than Kolmogorov-Smirnov. So that's the test power matrix. You look at the distributions. So for instance, over here we are comparing multi-Gauss with beta of some parameters, and they are easy to distinguish because the test power is almost 1. There are some of them that are difficult to distinguish. So what we are looking at is the sample size 250, significance level 0.5, as you can see on the diagonal. The average power is 80%, 0.8, and this is Kolmogorov-Smirnov. So in general, you want to see as many yellow places in this matrix as possible. So this is KS, this is topo test. So as you see, the matrix is more yellow. We can distinguish more. The average power is, I think, 0.9 over here. So where's the average power? It's here. 0.9 compared to 0.8 for Kolmogorov-Smirnov. We are able to distinguish more. And we actually tested many more possible distributions. That's the general pattern that we observe. I think this is for 2 sample. And this is still 1 sample. Oh, this is still 1 sample, but this time we are in the dimension 5. So this is where I only show the topological test. So we take 500 points in 5-dimensional space, trying to distinguish those distributions. Of course, the higher the dimension and with that amount of points, we only get 85%. But in this case, after a few weeks of computations, we just gave up on the Kolmogorov-Smirnov, so we never actually get a similar matrix for KS. Topo test, it wasn't all immediate, but it was pretty quick. So that already shows that we can try to attack problems which are a bit higher in dimensions. So over here, that's another type of comparison. So we fixed, one of those and one of those. And we check how the power of the test is growing. So once again, I may say it again. So we fix one of the distribution and one of the alternative distribution. We start to compare them, but we are showing the test more and more points. And what you expect is that if you have more points, and the power of the test should not go down. It should stay the same or go up, right? And that's what we see over here. So we have the power of the topo test in blue and the power of the KS in orange, I believe. And in all the cases for different dimensions, dimension 1, 2, 3, and 5 is monotonic as we expected. I think that there was some mistake over here. We are always above the Kolmogorov-Smirnov. So this is the general trend, regardless of the distributions. And yeah, that similar story also holds for the 2 sample problems. I won't get too much in details into this, just to mention that 2 sample is very expensive. You may be able to see it at some point. So that's the topological tests. So we have some theoretical guarantees, and we are able to work on the samples of reasonably high dimensions. I think that's the bottom line what I was trying to say over here. And I can briefly show you some of the code. So they're in the different folder, and I'm sorry about the mess. So let me start with one sample topo test. Keep it over here. So again, if you don't have it installed, you just put a explanation mark pip installed topo test. Let me include the variables. And what we are doing over here is we are trying to compare standard normal. So we are looking at one-dimensional distributions. You are comparing a standard normal distribution with a t-student with 3 degrees of freedom of the sample size 100, significance level alpha equals 0.5. So actually, those you can actually read the description of what's going on. So let me fit transform the topo tests. And what we are doing over here, so when we are fitting normal and comparing to normal, and we don't reject H0 very much as we expected. But over here, we are just fitting a sample of a t-student distribution. And it rejects. So the topo test see a difference between t-student with 3 degrees of freedom and the Kolmogorov Smirnov, and I think the KS did not reject it. Yeah, so KS did not reject it. So that's again one of the examples where topo test is a bit better. Over here we can just do the Monte Carlo. So we resample multiple times, and we get an average power in t-student with 3 degrees of freedom versus normal. For topo test, the average power is 61% roughly. Then over here we can compute the average power of the KS, and it's 12%. So again, that's the type of problems where we have an upper hand. But then we can again go to the higher dimensions. So over here we have normal distribution centered and zero with diagonal covariance matrix, 250 points. And then we have multi-value T with 7 degrees of freedom. And, I think topo test to reject, we are not doing KS over here due to the lack of so yes, we are able to reject it. So I think we haven't done the KS because of the time constraint. So that's what you can do with one sample tests. We have an analogous for 2 sample, and I'm not sure in the interest of time, you can feel free to play with it. What I may want to show you is another version of a 2 sample problem when we actually are looking at the problem in the spatial statistics. So there is a data set, and both in the paper and in the notebook, you can have a reference. So we are looking at the city of Rennes in France, and we want to verify if the distribution of some facilities like school, pharmacies, medical doctors, and clothing stores in the city of Rennes is the same distribution or maybe different distributions. So we'll have you can see actually those in the city border. So this is a spatial statistics problem, which we have over here. And over here we'll be using 2 sample problems. So you'll see that some of the execution takes more time. So let me run it. So over here we are just curating the data. let's do the 10,000 iteration in this bootstrap for the two sample problem. And then we are looking at all the pairs: stores versus schools, stores versus pharmacies, stores versus medical doctors, and pharmacies versus doctors. So let me run them. So you see it's taking a while to actually execute, because we are doing this 10,000 repetitions. But again, the feature of the topo test is that in standard literature, the tests think that all those variables, all those facilities are distributed according to the same cumulative distribution function. Topo test actually shows a difference in one of the cases. So it rejects the hypothesis in one of the cases. We haven't explored it further, but from our belief and from the previous experiments, we can see that normally it outperforms the standard method, and the method used over here is based on two names. Okay, so it didn't reject the first one. Is doing the computations of the next one, but one of them will be rejected. I think it was the stores versus medical doctors, or one of them. So we wait a little bit, we may be able to see the results. So once again, in this case, topology does have an upper hand, so I will let it run. I mean, normally it should take about a minute per distribution. So over here you have those other characteristic curves of those facilities, and as you see, maybe the pharmacies and the schools, which are not rejected because they are pretty close. Okay, so that's stores, schools are the same, stores, pharmacies looks the same. Yeah, so we are still waiting on the other two to finish. Oh, I haven't run this one yet. So we can come back in a second. So this is an example when this machinery can be used in the spatial statistics. So it's pretty general toolbox. You can install and play. So I mean, the spatial statistics is something which kind of makes sense. But if you look at, from my very pragmatic perspective, if you look at one sample test, it kind of looks fake. And what do I mean by looking fake? Well, we are working with biologists, with medical doctors, with engineers. And the probability that the biologist will come to me with 10-dimensional data set and give me exactly the formula for the cumulative distribution function, I mean, that will never happen. So I'm not sure if you agree with me, but practical use of one sample is kind of restricted. Well, I'm trying to show that this is not, because otherwise I wouldn't be putting it up, right? So let me try to show you that that's not the case. So if you think about philosophically what we did in the topo test, we don't need to know the formula. We need to be able to sample from a distribution. And that's a big difference, because when speaking about samples, we can think about the anomaly detection. And that opens up pretty big field. So let me give you one example. We actually are working on with one of the Polish bigger company. It's actually a mining industry. They are copper mining people. And they are interested in the problems of anomaly detection or the damage identification in the big machines. So for instance, they have a lot of those. It's called crusher. Not the no more daddy's joke. Star Trek, there was, shut up, Wesley. Think if you ever watched Star Trek, who knows what I'm speaking about? Let's see if this is a generational thing. It's a crusher, but I'm not speaking about Wesley Crusher. Got you. Okay. At least there's one. Thank you. Shut up, Wes. Okay. So the crusher is a big machine. It's essentially of the size of a building, and it has an input over here, and it has an output. So you have big rocks at the input, and there are small rocks at the output, and it's actually crushing the rocks. So if you want to extract copper from rocks, you want them crushed. So, there's a lot of vibration, a lot of, shaking happening over there. And typically, if you look at the vibration sensor, the signal looks like this. So it's very, very impulsive. And the impulses is when, a big rock falls inside, you expect it to shake. The problem is, in the unhealthy case, it may be the case that there is some cyclic impulse included. So it's very much like you're riding your bike and you hit something and then you get this noise and beep, 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 periodic noise. That's pretty bad. So this is what we want to detect. The problem is that the amplitude of this noise is typically so low that it's so hidden somewhere in the, in this vibrating thing. But that's exactly the case where we have a historical data, because those things they work for many years until they break. So we have the historical data. We know what's the signal, how it looks like. So we can actually sample from the distribution without knowing the formula and build the topo test. So that's kind of what we did over here. There is a subtle difference, and I won't go over the detail. But we were able to sample from this distribution, construct this blueprint, and then look at the standard deviation, how far away normal signal is getting from the blueprint. And then if something is broken, we may be able to detect it. Are they alive? Okay. Be careful. I mean, be careful in bringing it back to Europe. Yeah, I haven't said it. Okay, so we actually did 3 types of testing of this method. So the test number 1 is on the synthetic data. So they look at something which is called alpha stable distribution, and they use it to generate a time series like this. And in this alpha stable distribution, it depends on the parameter alpha, which varies between 2, going from 2 down to 1. So it's kind of a reverse order. So I didn't put up the formula, but alpha stable distribution for alpha equals 2 is just a normal distribution. But if the alpha approaches 1, it's getting more and more impulsive. And over here we input the amplitude of the cyclic impulse. So this amplitude. So how far it goes. And of course, the lower the amplitude, the harder it is to detect a cyclic impulse. The higher the amplitude, the easier it is. And those are the test power. So of course, those people are using some tools, and the tools they are using, it's called the CVB. It's a spectral method based on the so-called spectral kurtosis. And this is the power of the spectral kurtosis to detect the cyclic impulse as a function of the amplitude and the alpha parameter in the alpha stable distribution. This is topo test. And we are slightly better compared to the state of the art. So that's some justification that maybe it makes sense to carry it further. So we went back to the engineers and they say, okay, now stage 2. So we are moving on the higher TRL. On the stage 2, they constructed that thing, test bench. And they have the rotating on different speeds, and they look at something that is broken, something that is not broken. So over here, it's not like in the crusher case. We don't have the historical data, but we're just trying to see, for instance, the PCA plot of the Betty curves discriminate the intact situation, which we are kind of, marked over here on the PCA plot with the dots, and the dots of different color. Different colors represent different speed of the rotation. From the broken case, which is with the crosses. So even in the PCA, you see a clear separation. Very simple support vector machine gives you 100% accuracy blindly without knowing the labels, or based on the training. Yeah. So it works on the different speeds on the test bench. We never actually got the crusher data, but we get some acoustic data. So this is actually from the actual copper mine in Poland. And that's the, how you call the stuff that is actually moving. So you put rocks over there and they are moving out. That's the thing. But there's a bearing over here. And there's somebody from the team actually recording the sound of the bearing with the smartphone. That's the type of the signal we get. And some of the bearings were broken, some of the bearings were not broken. Our task was to detect the broken bearings. Here are the results. So first of all, you can see that there is a huge noise, huge variation. Those are real data from the real copper mine. CVB is pretty good. DDA works better. But I think the good news, and then something that the message that we are trying to put across is that if you actually combine topological features with the spectral methods, the results is even better. So we are getting kind of an orthogonal information, which gives us hope that there is something we can add to the game. That's verification on the real data. Unfortunately, we don't have yet the crusher data. I really would like to have this big machine thing. Okay, so this is an example where we actually trying to, the fact that we can sample from an unknown, in this case, cumulative distribution function, allows us to make this one sample cases a little bit more practical. Because we do not need to know formula, only need to be able to sample from it. Okay, so let's see, I have 15 minutes when I want to change gears a little bit. So tell me, are there any questions? Who wants to ask a question? Very good. There you are. Yes, SVM is the super vector machine. Linear, yeah, the simplest one. And then again, our punchline is interpretability. I mean, you cannot have anything more interpretable than this, right? Any other questions? Let me try another one. Any other questions? What do you mean exactly? Maybe we have a multi-class classification problem. Mm-hmm. Uh-huh. So like a multiple hypothesis testing? I mean, I think Rafael done something in this direction, and I can ask him what he done. So yes. So a person in my group who is a statistician by training, he did something, but I'm not sure if I'm able to repeat it right now. Yes, so something in this direction has been done, but I'm not competent enough to answer this question. But if you want, drop me a line and I'll put you in touch with the right person, okay? Okay, any other questions? There you are. Okay, so may I have another question to a statistician? So are you doing cross-validation in the goodness of fit tests? That's not something you do, right? It doesn't make sense. No. Yeah. It's a different story. So we are not doing okay. So the point over here is we kind of swapped over it pretty quickly because it's quite technical, but we do have a theory behind it, at least in the when the sample size goes to the infinity. So it's not machine learning. If you have a machine learning, then you do the cross-validation in order to make sure that your results are not because you were very lucky in selecting your training and test split. Over here is a bit different story, so it's more statistic-ish. Again, normally, if we are speaking about using topological features in classification, of course, you need to do proper cross-validation, train, test, and there may be split into at least two or maybe three different groups. This is what we are doing, and that's very standard, yes. But not in the that's another type of problems that we are facing over here. Okay. Any other questions? Okay. So I spent all my time so far speaking about the features of the data, potential use of the features of the data. And so if we go back to the motivation, started from Anscombe's quadrat or the Datasaurus data set saying, well, standard summary statistics don't see a difference. We can see the difference with our eyes. So there were two conclusions. Maybe you need some stronger things to add to the summary statistics, and we did propose a few of them. But another one, and that actually goes back to the original Anscombe's paper, always visualize your data. So that's what I want to talk about. So we are going into the visualization method. So yeah, I put some, so for instance, I mean, if we compute persistent homology of those two clouds, it would be quite similar, but you know, we want to be able to detect features which are kind of contractible, like the flares, contractible into the main body of that, whatever this creature is. And there are a bunch of algorithms. So everything started, okay, so I'll have enough time to do the standard mapper. Okay, so everything started with the concept of the rep graph. It goes back to 1940s, 1950s. Rep, he was French, therefore it's a rep, not a rip. If he was an English or American, it would be rip, but he's a rep because he's French. Make sense? All right. So we have a rep graph. And in order to define a rep graph, we need a nice manifold, M. And we have a nice smooth function on that manifold. It's a Morse function, a standard Morse function. And I think I have a yes, I have a definition over here. So we define an equivalence relation. So if we take two points from our manifold, we say that they are equivalent even only if the following two conditions are satisfied. So condition number one, they need to have the same value of f. And the condition number two is they need to belong to the same connected component of this fiber. Okay. So let me go back to the picture once we have it. So in the picture, you know, there's a standard Morse theory type illustration. You always have a stand-up torus. Nobody will dare to lay the torus flat. And there's a good reason for that. If you know the reason, you know. If you don't know the reason, you can ask me later. So we have the standing up torus. Our function is the z coordinate. So the values are over here. And if you look at the inverse image of the values, I mean, in this range, those are kind of ellipsoids. Also ellipsoids over here between this and that critical points. But if we are looking at that range, I mean, they have two connected components. So everything between here and there, I mean, this condition is satisfied immediately because those fibers has only one connected component. So the points are equivalent if they have the same value of the function, and therefore we have only one abstraction class. But for the points in between, you know, those critical saddles, we have two connected components, and therefore we have two classes of abstraction. Oh, I didn't define a rep graph. So a rep graph is just a quotient space M quotient by this equivalence relation. And this is what is illustrated in red. So that's the rep graph of that manifold with the function. So that's a very classical thing. It's 70, 80 years old. And back roughly in 2007, a group of people from Stanford, Gunnar, and Facundo and Gurjet was asking a question. What happens if we don't know this manifold as a continuous object, but we only know it from a finite sample? So it's like a manifold having a chicken pig. This is, we know the function exactly, but M is only given from a finite sample. Okay, can we get something which reassembles the concept of the rep graph? And then they actually proposed this construction, which they call the mapper algorithm, which, if you look at the definition, it kind of tries to mimic this definition. So let's take a look at how the standard mapper is constructed. So this time we have a finite collection of points sampled from our manifold, and the function again on this again manifold, which we evaluate on this collection of points. And we define a relation between points. It's not equivalence relation anymore, but 2 points are in relation if their values, well, okay, first of all, over here we ask for the values to be equal. And in practical case, if you have a finite collection of points, this will never happen. I mean, if it happens, be careful about your data. That smells bad. So we need to relax it a little bit. It cannot be equal, but it should be close, whatever it means. And I mean, concepts of connected component doesn't make sense because we only have a finite collection of points. So we need to replace it by something, and they propose to replace it by belonging to the same cluster. Okay, so that's pretty unspecific. So let's work on this. So what Gunnar co-authors proposed was how to measure if the two values of the values of 2 points are close. Well, they propose to look at this projection and cover the range of the projection with a collection of overlapping intervals. And well, simply the values are close if they end up in the same interval. If there's one interval, they may end up in the intersection of 2. But if I can find one interval, the f of x and f of y are landing up in, then I do consider them close. Otherwise, they are not close. So that's the first thing. But then there is this this part. So we look at the inverse image of a fiber when we have a natural candidate of the fibers over here. Those are the cover element. So I can look at all the points that are mapped by my function to this cover element. And I want to look at something that reassembles the connected component of this set restricted to that stripe, which maybe, well, I run the clustering algorithm of my choice. So you have a lot of freedom over here. But once you have the clusters, we are simply checking if x and y belongs to the same cluster. If they do, then they are in the relation. If they don't, they are not. So over here, it's pretty obvious to expect that we expect to see 2 clusters. Maybe over here, we expect to see 1 cluster. And you know, what we are doing is, this way we are getting a cover of our data. And yes, and we are building the finite graph, which in a certain sense converges or is an estimator of a rep graph. If you want to know more, there's a very nice work of Steve O'Donnell and Matthew Carrier on this. Can give you reference later. So that's a standard mapper algorithm. We'll do some of the examples. I'm not sure if today, but maybe definitely tomorrow. So let me just kind of summarize it. So what we need is, yes?
The mapper is the nerve?
Yes, one-dimensional nerve of the cover we are getting from those clusters. Yeah. Okay. Any other question? Any other question? I mean, there are some relations, and I'm thinking about it for like 10 years. So I think it would, but nothing came out yet. Yeah, but let's talk. Maybe not today, maybe tomorrow morning, but let's talk, all right?
Is there any reason why you want to restrict the point?
Yeah, yes. So it's a visualization method. Yes, so the reason is Whitehead's theorem. So if I have a graph, I can, so the Whitehead theorem tells us, for those of you who don't know, if I have an n-dimensional complex, I can embed it into 2n plus 1 dimensional space. So if I have a graph is one-dimensional complex, so 2 plus 1 is 3, and that's something I can visualize. But if I go with, if I include, for instance, triple intersections and want to add triangles, and in the worst case, I need 5 dimensions, and simply visualization of that thing may be problematic. So that's the only reason why we restrict to binary intersections. But if you can see in 5 dimensions, you don't need to. Or if you want to use mapper in another way, and there are also people doing it. So for instance, sparse ribs is essentially that thing. Then you can go higher. You want another one?
Maybe if you could write two skeletons and then
I mean, yes, there are various ways you can try to do it. It's just it's not doing in a standard way. I mean, yeah. Any other questions? Yes. So say again the question. No, n is the dimension of the complex. It's not the number of vertices. The Whitehead's theorem. So tell me the Whitehead's theorem you know. That's not Whitehead's theorem. I mean, many graphs are planar, so you can embed it to R2. Those which are not planar, you can easily embed it to R3 without set intersections. You don't need more dimensions than 3. Oh, so you want not only geometrically but also isometrically embedded. Okay, that's another story. We are not speaking about isometric embeddings. Okay. There was one question somewhere here. Tell me. No. So, that's both the blessing and the curse of mapper. The blessing is you can use pretty much any clustering algorithm you want. And the curse is you can use pretty much any clustering algorithm you want. So you need to make a choice. Yeah. No, this is precisely what Jesus was asking. So, we leave this room for the intersection so that clusters may allow to intersect. Because if the range, the cover of the range intersects, that we allow, for instance, the clusters to intersect, and therefore one-dimensional nerve may actually have some edges. If we don't allow for the intersections, then they will be distinct. There will be no intersections, and your graph will be just, having as many vertices as you have clusters, extremely boring. Okay? Any more questions? I think I'm out of time, so let's see. So let me. Okay, that's a good point to stop, and we'll restart tomorrow from that point. Thank you very much for your time.